Continuing on with our learning objectives, we'll move to understanding and describing hydraulic retention time. In the introductory lesson of the Bioreactor Basics module, we learned about the 4 things necessary to have a bioreactor work. Now, in these next 2 video lessons, we're digging a little deeper into related but distinct factors that impact how well a bioreactor removes nitrate. So now we're not just talking about having denitrification occur, but how to actually maximize that process. And to tie to our last lesson, DO and ORP were not specifically on this diagram, but of course they underpin bioreactor function, because you know by now we're looking to achieve those anoxic conditions. And DO and ORP both influence and are influenced by these factors. I started trying to draw these arrows, but it got super complicated, so just know that these themes are all very interconnected for our bioreactors. The first concept we'll talk about is the engineering concept of hydraulic retention time, or I'll often say HRT. This is a concept that's often used in the design of bioreactors and has important impacts on reactor function. But before I go through this equation, I want to talk about hydraulic retention time in more of a conceptual way. We'll start with this overview image of a bioreactor, and imagine, if you will, that you are a parcel of water entering this bioreactor. In this first conceptual example, we have 5 milligrams per liter DO and 15 milligrams per liter nitrate coming in. I just made those numbers up for the sake of an example, but you see here in the first zone, labeled the aerobic zone, this is where that DO is being consumed by aerobic bacteria. They're eating the carbon in the wood chips and breathing or reducing that dissolved oxygen in the water. The carbon's being oxidized and the oxygen is being reduced. Remember, aerobic reactions involving oxygen will be performed first because they generate the most free energy. Once the DO is consumed, at some point along the length of the reactor, there's no more DO in the water and the water enters into an anoxic zone. This is where the DO is 0 and the ORP is in the right anoxic range for denitrification, and we start to have nitrate concentrations go down. So in this hypothetical example, the nitrate concentration decreased from 15 to 3 across the bioreactor, but you see that doesn't actually occur until you're in the anoxic zone. I labeled this as a pretty ideal example of where the flow rate in this given bioreactor size was just right. This next example is where the flow rate is very high for the given size of the bioreactor. If the flow rate is high and the water is just slamming through the wood chips, that means the time the water stays in the bioreactor could be too short. That is a retention time that is too short. In this case, we have the same water chemistry coming in as our last example, but now the water is moving faster so that the aerobic zone is much longer. It takes a longer distance of wood chips to get that DO down to the anoxic range that we need. And that impacts bioreactor performance because our anoxic zone then becomes very short and we don't get as much nitrate removal at the end compared to that first example. This last example is where the flow rate is very slow relative to the size of the bioreactor. Imagine the water is just trickling through the wood chips, and that means the retention time of that water is very long. You see the same initial water chemistry, but here the water is just trickling, so the aerobic bacteria consume that DO in a very short distance. You see the just right anoxic zone there in the middle where denitrification is occurring, but the difference in this example is that all the nitrate gets removed before you get to the end of the wood chips. So I've labeled this as wasted space, which it is from the perspective of denitrification because there's no more nitrate to remove. But remember, this is still full of carbon, which fuels a ton of different biological processes. After all the nitrate is removed, the conditions continue to become increasingly reduced, and so you move into processes like sulfate reduction or even methanogenesis. Put differently, the bacteria that reduce sulfate start to outcompete the bacteria that reduce nitrate because there is no more nitrate. Those are processes that we don't really want because it wastes my carbon, which I put in there specifically to fuel denitrification. And 2, hydrogen sulfide isn't very good. It smells like rotten eggs and it's toxic to aquatic life. Also, methane is a greenhouse gas. We'll cover those ideas more in the last video in this lesson module. So just to illustrate this process, I added the sulfate concentrations into this last example, and you see the sulfate reduction doesn't happen until you achieve highly anaerobic conditions that are very reduced. and that happens under very long retention times. So now that we have a feel for what retention time means in kind of a conceptual sense, let's go through the actual equation, which is pretty simple. Hydraulic retention time equals the porosity of the wood chips times the saturated volume of the wood chips divided by the flow rate. This equation lets you calculate the hypothetical length of time it takes for one parcel of water to move from the inlet of the reactor to the outlet of the reactor. And it helps you relate volume of the reactor, which is a design criteria, to the flow rate that's coming from the field. The rho in this equation is the effective, or usually more often, the drainable wood chip porosity. We'll talk a lot more about this wood chip porosity in the wood chip video coming up later in this module. V is the active volume of the bioreactor. By this I mean the length times the width times the saturated depth of water. The saturated depth is usually different from the total depth of wood chips because we rarely saturate the bioreactor up to the top of the wood chips. Usually only 1 to 2 feet are saturated in our bioreactors, whereas we might have a 3 or 4 foot depth of wood chips. Also note that the total excavation depth could be greater than either of those other two depths. In the HRT equation, you only use the saturated depth because that's the only depth that's actually contributing to flow treatment. You'll note that the numerator of porosity times flow volume or active volume ends up being the pore volume, which is the total volume of all of the pores in that given space. In the denominator, Q is the flow rate through your bioreactor. This is usually in liters per second or gallons per minute. Just make sure your units cancel out right because we normally talk about retention time in hours or sometimes days. We talked about the impact of flow rate in our previous examples. When the water is flowing really fast for a given bioreactor size, the HRT will be low and vice versa. Mathematically, this is easy to see because flow rate is in the denominator. So a bigger flow rate means you're dividing by a bigger number and you end up with a smaller HRT. In our tile drainage reactors, we don't really control the flow rate. We take whatever is coming from the field, and sometimes we even need to bypass flow. So while we don't control Q in this equation, from a design perspective, we do control V. And mathematically, you can see that if you have a much larger bioreactor volume, any given flow rate would stay in there longer compared to a smaller bioreactor. A larger numerator gives you a larger HRT. So let's do an example. Say we have a bioreactor that's 2 meters wide and 15 meters long, and I know that I'm managing the water level inside at about half a meter. I happen to know the wood chip drainable porosity is 45%, and today my flow rate is 30 liters per minute. One note about the water level, I'm assuming this water level in the entire bioreactor for this example. But we do know that this is not exactly true because there is a head drop near the inlet. In general, the outlet stop log level sets the level of water or sets the saturated depth, but I do want to point out that there is typically a head drop near the inlet. Let's plug our numbers in, 45% times 2 times 15 times 0.5. And then you see I flip the flow rate, so L is on the bottom. That's because I'm dividing by Q, so divided by 30 liters per minute. I work the math on the first part and calculate my pore volume is 6.75 cubic meters. That's the volume of all my pores in the flow area of my bioreactor. And then I add some conversions on the end, and my resulting HRT is 3.75 hours. What if we double the size of the bioreactor, making it rather than 2 meters wide, 4 meters wide? Would the HRT be higher or lower than our first example? Also higher than the 3.75. My point is that HRT is a factor of both flow rate, which we usually don't control, and bioreactor size or volume, which we control through design. So what is a normal range for HRTs? We did this global review of full-size bioreactors not too long ago, and the HRTs were reported most often less than about 2 days. Note the y-axis is a log scale in this graph. The median HRT was right around 1 day. Now that global review showed much longer HRTs actually than many of the bioreactors I monitored in Illinois, where the flow-weighted annual HRT, or the HRT at which most of the water was treated on an annual basis, that flow-weighted HRT was around 3 to 10 hours. So most of our flow being treated was right around that probably 2 to 8 hour range. A pretty clear trend from a variety of bioreactor studies is that as the HRT increases, so does the nitrate removal efficiency when it's assessed as a percent from 0 to 100%. This percentage is the mass of nitrate removed divided by the mass of nitrate that has flowed in. It's in minus out divided by in, and that's pretty much the same for anything you're treating when you're calculating removal efficiency for a pollutant. This trend only goes up to 100% because you cannot remove more than 100% of a thing, and at that point, your bioreactor is nitrate limited. Here's another HRT study that was done with smaller scale reactors, and you see that even though the HRTs were much shorter than that last example, there is a relatively linear trend with percent removal efficiency. One more example, this impact of HRT on nitrate removal efficiency, or percentage removed, was recently documented in a global review of all bioreactor studies, including lab scale, pilot scale, and full scale bioreactors. Looking at the medians here, those median percentages increase as you increase the HRT, moving from the left of the right to the right of the graph. This global review also allows me to highlight another metric. Rather than removal efficiency, this graph on the right shows removal rate. A rate always has a time unit as a part of it, and in this case, the units are mass of nitrate removed per volume of bioreactor per day. There is a relatively consistent trend of decreasing nitrate removal rate with increasing HRT. This makes sense because when the water is just trickling through the bioreactor and the HRT is really long, there's just not a lot of nitrate coming into the bioreactor to be removed. So you could be removing 100%, but your removal rate in terms of grams per cubic meter per day is pretty low. This older work here shows the same trend for wood chips as well as other carbon media. You have higher nitrate removal rates when you have a lot of water and a lot of nitrate coming in at higher flow rates. And those higher flow rates correspond, of course, to low HRTs. To wrap up, I'll make a few additional points about the concept of hydraulic retention time. Firstly, this concept of HRT is exactly the same concept that's used for other types of wastewater and water treatment reactors, as well as constructed wetlands, CWs. While the concept of HRT is extremely useful and one that I use all the time, it is unfortunately also somewhat erroneous. The assumption that the entire reactor volume contributes equally to flow treatment is simply not true. Wow, wow, wow. In large part because of variation, in our case, in wood chip porosity. For example, the porosity of wood chips in a bioreactor varies in 4 dimensions, along the length and width due to flow patterns, with depth according to saturation level in the bioreactor, and also across time. That's 4 different dimensions. And we rarely know the effective porosity of wood chips inside a bioreactor. We can do a good job of measuring this in the lab, but that's different in the field. Nevertheless, despite these pretty important limitations, HRT is still an extremely useful way to talk about bioreactor design and to normalize between bioreactors that are different volumes and flowing at different flow rates. It's an important way that we can normalize across studies. See you next time.